Okay, so I've got our synchronous alternator now connected as a synchronous motor. So basically, instead of applying power to the rotor and inducing a current into these armature windings, we're going to apply a current to those, and then we'll also apply a DC to our rotor to make our magnetic field and get that to get that motor up and running. Okay, so what I want you to pay attention to, the first video we're going to do here, I'm just going to start this and show you what happens when you first start a synchronous motor. These synchronous motors have an amortisseur winding, which is the same as a dampener winding in an alternator. Amortisseur and dampening mean the same thing. So when we first energize this motor, it's going to start as an induction motor. And then once we energize the magnetic field on the rotor, we're going to see that motor snap into synchronization. Okay, and what I want you to pay close attention to is the current draw for this motor. Okay, so when we started as an induction motor, you'll see a higher level of current, and then once we get that motor to lock into synchronization and run as a synchronous motor, you will see the line current to the motor drop, because now it's not going to be consuming any VARs from the system anymore. The only thing you're going to see on the ammeter is the amount of watts, or the amount of in-phase current that it takes to actually turn the machine. All the VARs and everything that are required in a winding are going to be supplied or going to be generated based on our rotor current. Okay, so I'm going to zoom this in. So we can see these values a little better. We've got our field current, so this is fed through our rectifier. We've got our field rheostat in series with it. That's our field current, and this is going to be our line current coming in. When we switch before we start it, this little switch here has got a resistance that is connected across those field windings, because when this motor is running as an induction motor, we've got a big coil of field windings spinning in that magnetic field. We'll get a voltage induced in the rotor, and we want to short that out so that we don't, when we energize it, we don't have a built-up charge in the windings and then try to send a charge back from our system. Okay, so I'm going to start this up. You'll see this motor's drawing 10 amps. Okay, and then when we energize our field coils and start applying a current to it, you heard it got a lot smoother, and then our line current dropped down to significantly less. And we're excited. So even when the field is under excited, we've only got 1/4 of an amp of field current. Our line current coming into this motor is 7.9 amps. Okay, so this is running under excited right now. That means that we're still consuming some VARs from the system, but not as many as when it was running as a pure induction motor. Now, as we decrease this field rheostat, we're going to increase our field current. I'm going to go up in 1/2 amp increments. We'll start at 1/2 amp. Our line currents drop down to 5. At 1 amp of field current, our line currents drop to 1.5. And now at 1.5 amps, our line current starts coming back up. So we're at 3 amps of line current, 1.5 amps of rotor current. go up to 2 amps of rotor current. Our line current has come back up to 7. Okay? So what we saw happen there is that when the motor was running running as an induction motor, so just running on the amortisseur windings, I think it was 15 amps, I'd have to scroll back and check, but it was fairly high. And then if we plot out, we made that synchronization, once we established that link, we saw our incoming current go down. So this is going to be our I line. Started out at 15 with 0 amps of field current. When we didn't have the field engaged at all, we had 15 amps, and then at should have wrote these numbers down as I was doing it, but I didn't. What we saw is as soon as we energized our field coils, that current dropped down. And then as we went from 0.5 of an amp of field current, this actually started dropping down significantly at like a quarter of an amp. Didn't take very much to establish the link. And then we saw based on our field current, we saw our line current started out at around 7 with half an amp of field current. We got down to about 2 amps, and then we came back up to 7 amps as our field current increased. So what was happening is the synchronous motor had a lot better power factor than the induction motor. That's what caused our first drop in line current. Then we started out with a really low field current. That motor was still running at a lagging power factor, so its current was relatively high. It was still 7 amps. As we increased our field current, our line current dropped. Smooth this out a little bit. Right? As we increased our field current, our line current dropped, and it hit a low spot of around 2 amps. So at that point, we had enough field current to have that motor running at unity power factor. Then as we kept exciting, or we over-excited our main field, we saw our line current come back up. So what was happening there is after we hit unity, as we over-excited the field, that synchronous motor was actually putting capacitive VARs back into the system. So on this side, it's producing inductive VARs, or consuming VARs, I always say. And then after we hit our low point, the bottom of the V curve, anything from here on out, we were producing capacitive VARs, right? There was more VARs created in the machine than what it needed, so it was able to send some back out to the utility or whatever. So that's what happens with a synchronous motor. Is starts off as an induction motor. Once we energize the field coils, our current drops. As we go from that minimal amount of field current that it takes to establish the DC link, as we increase our field current, we see our line current drop because it's consuming less and less inductive current. start to produce its own inductive current within itself. We get to a low point where it's creating exactly enough inductive current to satisfy the windings of the motor itself. And then as we overexcite that field, we see our line current come back up, because now we're still producing inductive current, but it's more than the machine itself needs, so we start sending that current back out to the lines. That's the operation of a synchronous motor.